So let's look at the double angle identities. So we have sine 2 theta is equal to 2 sine theta multiplied by cos theta. So we call this a double angle because we have over here 2 multiplied by the angle theta, and double just means multiplied by 2. Then we have for the cosine, cos 2 theta is equal to cos squared theta minus sine squared theta. Now actually for cosine, there are 2 more double angle identities. So we have cos 2 theta is also equal to 2 cos squared theta minus 1. And finally, cos 2 theta is equal to 1 minus 2 sine squared theta. So these are the 3 double angle cosine identities. So for the tangent, we have tan 2 theta is equal to 2 tan theta over 1 minus tan squared theta. Now, because we have 3 cosine double angle identities, we have to be careful which one we use. So if I knew cosine, the value of cosine theta and sine theta, it doesn't matter which one we use. Using any of these 3 would give me the same value. Now, if, for example, I only knew the value for cosine theta, then this is the one that I would use. If I knew the value of only sine theta, then this is the one I would use. So with some practice, you'll be able to quickly determine which of these is the one that you're looking for. So for example 1, we're asked if sine theta is equal to minus 7 over 25 on the open interval pi to 3 pi over 2, find sine 2 theta, cos 2 theta, and tan 2 theta. Well, let's firstly recall that sine theta is equal to y over r, but we know what sine theta is. It's over here. So I'll write this down over here. And then we'll know that y is equal to minus 7 and r is equal to 25. How do I know that this negative sign here belongs to the y value? Well, r stands for the radius, and radius is a measure of distance, and distance can never be negative. So this has to be a positive value, and that's why this negative sign belongs to the y value over here. Now, we want to draw theta in the standard position using the quadrant diagram. So we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. This is our first quadrant, second, third, and fourth. Now, because we are interested in the interval pi to 3 pi over 2, that's the third quadrant over here. So if we draw in our angle theta in the standard position, it would lie in the third quadrant. So we know that the point lies in the third quadrant, and its distance from the origin is 25 because r equals 25. Now, this vertical distance here is 7. How do we know that? Well, we know the y value is minus 7. So along the y-axis, minus 7 would be here. But I'm only interested in the distance from the x-axis, which is 7. Now, I want to know what this distance is over here. And we can notice that this is a right angle triangle, so we can use Pythagoras' theorem. And when we use the Pythagoras theorem, we know that this distance over here is equal to 24. So we'll just put that in there. Now, we know that the x value is going to be equal to negative 24. How do I know that? Well, we can see here, this part lies within the negative part of the x-axis, so we must put down the correct sign. So this is a negative 24. Now, we should recall that cos theta is equal to x over r. We know what x is and we know what r is, so we substitute them into here to give us minus 24 over 25. And also we should recall tan theta is equal to y over x. Now, we know y value, we know the x value, and we simply substitute to give us 7 over 24. And because they're both negative numbers, and when we divide two negative numbers, we'll end up with a positive number. Now, if we recall the double angle identity for sine 2 theta is equal to 2 sine theta multiplied by cos theta. We know what sine theta is, we know what cos theta is from here and there. We simply substitute them into this identity to give us the following. And when we compute this, we get the simplified answer of 336 over 625. So now we want to find cos 2 theta. Now, because we know both sine theta and cos theta, it doesn't matter which of the 3 double angle identities we use. But in my example, I'm going to use this one. Cos 2 theta is equal to cos squared theta minus sine squared theta. And we know what cos theta and sine theta are, so we'll simply substitute into here to give us the following. And when we compute this, we'll have the simplified answer of 527 over 625. Now we'll find tan 2 theta. So we should recall that tan 2 theta is equal to 2 tan theta over 1 minus tan squared theta. Well, we know what tan theta is. It's 7 over 24. So we can simply substitute this over here and we'll get the following. And if we calculate this and compute this on our calculator, we'll end up with a simplified answer of 336 over 527. And again, there are alternative methods. With practice, you'll find out which is the most efficient method to use. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. Now let's look at the power reducing identities. So we have sine squared theta is equal to 1 minus cos 2 theta over 2. So why is it called a power reducing identity? Well, on the left hand side we have a power term, sine squared theta, and we've replaced it on the right hand side with a term which is a non-power. So this is why it's called a power reducing identity. So now we have cos squared theta is equal to 1 plus cos 2 theta over 2, and then the final power reducing identity is tan squared theta is equal to 1 minus cos 2 theta over 1 plus cos 2 theta. Please be sure to make a note of these three power reducing identities. So for example 2, we're asked to solve this equation over here. So this is the original equation, and we can see there's a power term here. So I'll just highlight that in red, cos squared x. And we should be able to recall the power reducing identity for cos squared x, which is cos squared x is equal to 1 plus cos 2x over 2. And we'll simply replace what we have here in red with what we have over here on the right hand side to give us the following. And then we notice that we have a term here with a denominator of 2 and a term here with a denominator of 2. So because they're both being divided by 2, I'm going to multiply both sides by 2 to simplify and give us the following here. Then I'll subtract 1 from both sides, and that'll give us this. And then we'll notice there's a cos 2x here, and there's a cos 2x here, so these are like terms. And when we simplify these like terms, we'll end up with minus cos 2x equals 0. I'll multiply both sides by minus 1, and that'll give us cos 2x equals 0. Now, the cosine of some angle is equal to 0. Well, we know from the original parent function of cosine that the cosine of some angle being equal to 0 is pi over 2 and 3 pi over 2. Therefore, 2x is equal to pi over 2 or 3 pi over 2. Now, we want to solve for x, so we simply divide both of these two values by 2 to give us x equals pi over 4 or 3 pi over 4. Now you'll notice in this question no interval has been given, so we can't stop at the answer over here. We need to write a general solution. So you need to remember that y equals cos 2x has period pi. So all we need to then do is simply take our value pi over 4 and add n multiplied by pi, and then take our value of 3 pi over 4 and add n multiplied by pi, where n is an integer. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. Now let's look at the half angle identities. So this is the half angle identity for sine. And it's called a half angle, you can see, because the theta, the angle, is being divided by 2. And halving something is the same as dividing by 2. Now, you'll notice there's a plus and a minus, and I'll talk about this in a little while. So this is the half angle identity for cosine. And this is the half angle identity for tangent. And in fact, for the tangent, there is 2 more half angle identities. This is the other one, and this is the final one over here. Now, there is some caution, as I mentioned. If you want to determine the appropriate sign when using a half angle identity, so if you want to determine whether to use the positive or the negative, because we can't use both, we have to check the quadrant in which theta over 2 lies, not the quadrant in which theta lies. So if you know what theta is, we want to know what quadrant theta over 2 lies. So here we have the quadrants, and this quadrant we can see we have the first, the second, the third, and the fourth. Now if you look at the first quadrant, all the trigonometric functions are positive over here. In the second quadrant, only the sine and its reciprocal cosecant is positive over here, and everything else is negative. And in the third quadrant, only the tangent and its reciprocal is positive. And in the fourth quadrant, only the cosine function and its reciprocal is positive. So let's look at an example. So say I wanted to determine whether to use the positive or the negative for this identity. So we're looking at the cosine function, okay? And we want to know which quadrant theta over 2 lies in. So if theta over 2 was to lie in the, say, fourth quadrant, we can see that the cosine function here is positive. So we'd use the positive. Now, if theta over 2 lied in the second quadrant, well, over here, only the sine function is positive. So that tells me the cosine function here is going to be negative. So I want the negative of this half angle identity. So please be sure to make a note of this. So in example 3, we're asked to solve this equation on the interval 0 and 2 pi. So here's the original equation. We can see we have an x divided by 2. So we have a half angle involving the cosine. So we need to recall what the half angle identity is for cosine. And that's what we have over here. So I'll simply substitute cos x over 2 and replace it with what we have over here on the right hand side to give us the following. And we need to remember to raise it to the power of 2, because over here the cosine function is raised to the power of 2. And when we raise what we have here in the bracket to the power of 2, we'd end up with the following. We can see whether this was positive or negative. When we square something, we'll end up with a positive. So we can see this is why the negative sign is gone, and we're left with a positive term. Okay, and then we can see a radical here, with this being the radicand, and when we square something, it undoes the radical, and we're left with this radicand over here. Now, we'll multiply these two by using the distributive property, and that will leave us with 1 plus cos x on the right hand side. And you'll notice now we have a cosine function on the right hand side here and a sine function on the left hand side. So this is a power term, so I want to replace this, and we can replace this by using another Pythagorean identity, which is sine squared x equals 1 minus cos squared x. So replacing sine squared x with what we have over here, 1 minus cos squared x, will give us the following. Now we can see that we have a single trigonometric function. We have a cosine here and a cosine here. Now we'll subtract 1 plus cos x from both sides, and that will give us minus cos squared x minus cos x on the left hand side and 0 on the right hand side. Now you can see there's a common factor of a cos x, so I'll take this factor out, and in the brackets we'll be left with minus cos x minus 1, which is equal to 0. And then from here we can use the zero product property and write down either cos x equals 0 or this bracket minus cos x minus 1 is equal to 0. And we want to isolate the cosine term over here, okay, and that will give us cos x equals minus 1. So we have two trigonometric equations we want to solve. So cos x equals 0, and we solve for x to give us x is equal to pi over 2 or 3 pi over 2. And then we'll solve for x over here to give us x is equal to pi. And this is our final solution, where x is equal to pi over 2 or 3 pi over 2 or pi on this closed interval 0 to 2 pi.